Hello. So, in today's class, we will try to understand the characterization of atmosphere based on the electrical properties. So, in the previous class, we have seen the thermal structure of atmosphere, wherein we have been able to identify various layers of atmosphere depending on how the temperature varies with respect to the height. So, at each turning point, we have defined one particular layer, then we have 4 different layers, which are the troposphere, stratosphere, mesosphere and thermosphere. Now, in today's class, we will try to see how we can discuss the electrical properties in the picture. Now, based on the electrical properties, we define what is called as the ionosphere. Ionosphere is an important layer, is also an atmospheric layer located from the upper mesosphere all the way into thermosphere. So, ionosphere is by definition is the region of the atmosphere where we have electrons and ions present in a large numbers, so that they can influence the radio wave communication. Now, the most important aspect is that in discussions so far, we have always seen that it is the nitrogen and oxygen in the molecular form, that means in the neutral form, are the major chemical species in the atmosphere. We have not talked about electrons, we have not talked about ions, anything like that. We have not talked about anything electrical in nature, that means any charge quantities in nature, right. Atmosphere, in addition to all the neutral species such as all the gases, is also home to various ions and electrons. So, this the region where these electrons and ions are present in large numbers is called as the ionosphere. Okay. So, ionosphere contains electrically charged particles called ions due to ultraviolet radiation. That means how these ions are generated. That means you have ultraviolet radiation, which is extremely energetic in nature. In the beginning itself, we have learned that ultraviolet radiation has the ability to ionize all the species that are present in the atmosphere in gaseous form. It also has the ability or the energy to dissociate all the molecules. So, ultraviolet radiation can dissociate molecules and ionize atoms. So, when you ionize an atom, let us say a neutral oxygen atom, so you will get an electron and ion. So, due to the action of this, you will have the ionosphere present at nearly, let us say, 50 kilometers or 50 kilometers to almost 300 kilometers. So, this height limit sets the beginning and the ending of the ionosphere. So, ionosphere is the region where electrons and ions are present sufficiently in large numbers to be able to influence or affect the radio wave communication. Okay. So, ionosphere acts as a reflecting layer for the amplitude modulated radio waves, making communication beyond the line of sight possible. That means, generally the communication is possible between line of sight reception points, right. So, if you want to achieve communication beyond the line of sight, then you have to resort to some radiation whose wavelength is sufficiently larger to be, so that it travels all the way from here to here. So, it is the ionosphere which acts as a reflecting layer on the top and makes the communication possible beyond the line of sight. And in addition, ionosphere creates the northern lights such as Aurora borealis, which you see in the northern hemisphere or northern pole, and the southern lights, which are Aurora australis, which is seen in the southern pole through interaction between sun's solar rays, solar radiation and the earth's magnetic field. So, you have many processes in which sun's solar radiation or plasma emitted by sun, when these things interact with the atmosphere or let us say with the ionosphere, releases photons, let us say, which are in the visible spectrum. Due to the interaction of solar radiation and solar plasma with the atmosphere, solar complex reactions can lead to the formation of visible photons, which you always see as air glow or aurora. So, this is a pictorial representation. Ionosphere is again divided into 3 different 4 different layers. Let us say the ionosphere is, let us say, is defined, let us say, into D layer, E layer, F1 and F2. Now, D layer is the bottommost, F2 layer, if it is existing, is the topmost. So, F2 layer is the one which experiences or which gets the complete energy from the sun, and D layer is the one which gets the least energy from the sun. Now, ionosphere itself is a complete module which we will take up at some point in this course, but I would like to make one particular point is that each of these layers have different set of physical and chemical processes which are responsible to create electron and ion densities in abundance. So, typically the densities that we are talking about is 10 to the power of 12 per meter cube, 10 to the power of 12 electrons or 10 to the power of 12 ions per meter cube in the ionosphere, in the peak ionospheric concentration. So, this is the peak ionospheric charge density. That means you have this many number of electrons or ions per unit volume. In this picture, what you see is this region is the shadow with respect to this transmitter. But if you have an ionosphere, the waves which are going towards the sky will get reflected, and they will travel in this in all directions, making it possible to communicate between this point and this point, right. Now, most importantly, why does the F layer reflect electromagnetic radiation, right. This is a very important physics question. I mean, this is a very important question wherein why reflection, how does reflection happen? No, it is very simple again. How does reflection, why does reflection happen? So, in electromagnetics we have seen that electromagnetic ray will get reflected when the refractive index condition between two media matches a particular limit, right. That is what happens here as well. Now, the point is the ionosphere acts as a conducting layer or acts as a mirror in the sky, which reflects the incoming radio wave signals from the ground onto the shadow regions. Okay. Now, this is the picture of the aurora. So, what you see is you see brilliant green color patches in the sky. So, if you are able to see, I mean the green color that you are able to see, so this must be visible photons in the green color, right. So, these photons or these emissions are the result of complex processes between solar plasma and Earth's magnetosphere and Earth's ionosphere. Okay. So, this is something about characterization of atmosphere based on the electrical properties, not based on the thermal properties, right. Now, several other aspects, let us say, pertaining to atmosphere and pertaining to the radiation, let us say, that is emitted or absorbed by the planet's surface and atmosphere. So, what you see is the components of Earth's atmosphere or the Earth system itself absorb and reflect sun's radiation by differing amounts. That means that not all the parts in the Earth system absorb equally. Some parts will absorb more radiation and some parts will absorb less radiation. Let us say if you look at this picture, what you will be able to see is that land absorbs very well. That means the incoming solar radiation is well absorbed by the land. Good. Clouds reflect well. That means clouds has the ability to reflect radiation away. I mean, so the clouds are stopping the solar radiation from entering into the Earth's atmosphere. So, typically the cloud tops, you always remember this number, the cloud tops exist at 10 kilometers, okay, and all the weather happens below 10 kilometers. So, all the weather happens below 10 kilometers, and fundamentally we know very well that all the weather is driven by sun again. So, that means that the cloud tops influence the weather very much. Okay. So, if there is a cloud, then there is no heat beneath the cloud and so many other things. But the point is radiation is stopped very well by the clouds. Okay. Now, sea, the water bodies absorbs the most. I mean, sea also absorbs very well. and what is remaining? The ice. The ice reflects the most. So, the point is objects or systems with white color reflect very well. Now, this discussion again brings us one more very important aspect. Some point we have seen that in the evolution of Earth's atmosphere, we have seen that there was a point when the CO2 levels were kind of decreasing because of the photosynthesis reaction, right. CO2 levels were decreasing because a lot of CO2 was converted into organic monomer, and at the same time it was also releasing a lot of oxygen. That means CO2 is getting lost from the atmosphere. So, when CO2 was lost, the global temperatures were decreasing because there is nothing to trap the outgoing infrared radiation. So, the global temperatures were decreasing. So, as the temperatures were decreasing, there was a definite possibility that the earth could have frozen, and it has actually happened that over 5 million or 50 million years ago, the entire earth glaciated, right. Now, what happens? Then I mentioned something called as a negative feedback system, wherein once the earth glaciates, you have the snow cover on the entire planet. Now, for it to come out of this glaciation process, it needs to get as much as energy from the sun, because there is no other source beneath the glaciers, right. So, there is no internal source for the earth system, we know that very well, right. So, for this earth to come out of the ice age, we need to have more radiation, and if there is a lot of ice on the surface, the ice has a tendency to reflect most of the radiation away. So, earth will not get heated up, and so this is a loop in which the more glaciers you have, and there is the radiation that you get is less, and as a result you will never get out of the glaciation. I mean, you will never get out of the ice age. So, it was a definite possibility in which earth could have forever fell into the ice age, and it could have never got back from there. But what happened? CO2 levels were of course decreasing as a result of photosynthesis reaction, but there was still a lot of volcanic eruptions which were active and which were continuously pumping enough amounts of carbon dioxide into the earth system. So, this increasing carbon dioxide, because of a source which are called as volcanoes, was only the helping mechanism which has actually thrown us or thrown the earth out of the ice age. Otherwise, the entire planet could have been a pile of ice, that is it. Okay. Now, so in this context, so what we see is we have we do not have anything else. I mean, we have land, we have the ocean, we have the clouds, and we have the ice. So, these 4 systems out of these 4 systems, 2 systems have the ability to absorb very well, and 2 systems have the ability to reflect very well, right. So, land and sea are there to absorb the radiation, and ice and clouds are there to reflect radiation. So, these 2 systems will try to decrease the average temperature than what it is today, and these 2 systems will try to increase the temperature by some extent, right. Now, here you define what is a very important parameter which is called as albedo. Albedo is the ability of a surface, let us say land surface or any kind of surface, to reflect radiation, to reflect light, that is it, right. Now, in addition to this land, cloud, sea and ice, you also have atmosphere or more familiarly called as air, right. So, you have air. Now, what does it do? It does not do anything, as in the column of atmosphere is transparent to visible and infrared radiation, we know that very well. So, so all the visible radiation and all the infrared radiation travels right through the atmosphere and it reaches the surface. Once it reaches the surface, these 4 things will come into picture and will decide how much amount of radiation is to be taken by the earth and how much amount of radiation is to be given away into the space. Okay. So, here, we can simply say that the ability of a surface to reflect light is called as albedo, and albedo is very high for cloud and it is very high for ice, and the albedo is very low for land and clouds, land and sea. So, as a result, what you can say is that we can calculate albedo by incidenting some radiation and again measuring what is the reflectance out of the surface. Right. Now, since we have earth, which is a combination, which is a very complex combination of these 4 different types of surfaces. So, the entire earth surface, the entire earth marble is made up of unequal proportions or time changing proportions of land mass, clouds, sea and ice, we have an albedo of the earth itself. I mean earth as a whole, how much of radiation, let us say if I throw 100 photons at earth, how many number of photons will be reflected and how many number of photons will be absorbed. So, this is called as the albedo of earth itself, the planetary albedo. So, the formal definition of albedo is the fraction of incident radiation that is reflected from a surface. You throw something, what is the fraction that you get back, or what is the fraction that the surface throws back or reflects back, is generally called as the albedo. And this value, since it is a ratio, it can be only between 0 and 1, that is it, it cannot be greater than 1. So, for a practical, let us say understanding, what you have is you have a limit 0 and you have 1. So, when the albedo is 0, that means no light is reflected, that is it. So, when the albedo is 0, no light is reflected, all of it is absorbed. So, we know that sea and land have the very good absorption capacity. So, they lie in the lower portion of this albedo graph, right, and the clouds and polar caps, they have the ability to reflect most. I mean whatever falls on them, it has the ability to reflect most of it. That means clouds and polar caps have higher values of albedo, and on the whole, let us say the earth's average albedo is 0.37. So, I mean we can say that it doesn't reflect much actually, right. So, this makes sense, both sea and land have very low albedos, right, and so it is mainly the sea cover that you see from the outside. You see the earth to be a blue planet, that is the sea that you see mostly. So, it has more ability to absorb than reflect. Okay. Clouds, of course, cloud cover varies with respect to time, it does not stay the same forever, right. So, the take home from here is that the planetary albedo for earth is 0.37, you remember this number always. So, you throw 100 photons into the onto the earth, you will get 37 photons reflected away, that is it, the remaining are absorbed. Okay. And the remaining that is absorbed is only the energy that rises the earth to 70 degrees Celsius average temperature. Okay. Now, in continuation, it is very important that we understand the greenhouse effect. So, what exactly is greenhouse effect? We have seen water vapor and methane and carbon dioxide, or we have named these chemical species as greenhouse gases, and we know to a very general understanding that these greenhouse gases are the ones which are increasing the average temperature of the earth, and these are the ones which are responsible for the very well known or very well understand concept which is called as the global warming, whatever it is. Now, greenhouses, let us say, what is greenhouse? Greenhouses maintain a higher temperature than their surroundings. So, you have a greenhouse, then the temperature inside is relatively larger to temperature outside. Why should you have a greenhouse? So that you can put delicate plants inside this house in the cold winter, so that they can sustain the winter, right. So, they achieve this due to their glass or plastic walls which let light in, which is largely absorbed by the plants and the surface inside the greenhouse. So, these radiate infrared radiation which warms up the air in the greenhouse, as a result, right. So, this sounds pretty similar to the situation that we have on the earth and in its atmosphere. So, which is why the term greenhouse effect is used. So, that means that you have made a mechanism in which more amount of radiation could come into the system, and as a result this radiation is kept inside this system, and because you have this radiation, the average temperature inside the system is larger. So, if you remove this radiation from this picture, the average temperature is significantly lower, I mean smaller. So, that means that this mechanism of holding this radiation is what is being replicated in a greenhouse. That is why you call it as greenhouse effect, right. So, there is an important difference, I mean there is an important difference, of course there is. So, although the air and the walls of a greenhouse do not absorb the infrared radiation, that is how they are made, the main reason that the greenhouse stays warmer than its surroundings is that in the winter is that its walls trap warm air, preventing cooling drafts. I mean, this is not there in the Earth system. So the Earth system is an open system. You don't put walls so that the warm air doesn't go beyond a particular point, beyond the wall. There are no physical barriers wherein you allow something and you don't allow something. So this is the major difference in comparison to the greenhouse and the greenhouse effect that we see on the planet Earth. Okay. Now, so the Earth's atmosphere is not exactly like a greenhouse. It's not completely like a greenhouse. It's of course it represents the effect is of course to some extent is true in the case of Earth, but the mode and mechanism in which this effect is achieved is not completely the same between the greenhouse and the Earth. Okay. So our atmosphere is relatively warm because it traps the re-radiated infrared radiation by absorbing most of it before it reaches the space. So it's basically you have this planetary surface and you have infrared radiation which is emitted from this surface, and this radiation is actually escaping into the space, escapes to space. That's what is happening. Now, if you put a trapping mechanism and don't allow it to escape to the space, what does it do? Infrared radiation is nothing but heat. This remains inside, right? So this is achieved in a different way. So here the warm air is trapped by physical barriers, and here the warmness is trapped by the greenhouse gases. So that's the basic difference. Okay. Now, among the other gases, water vapor, methane, and to some extent carbon dioxide and certain other gases in our atmosphere are very good absorbers of infrared radiation. So they trap much of the re-radiated energy inside the atmosphere. So that's what they do. So the result is that the Earth is significantly warmer than it would be without an atmosphere. So I mean, greenhouse effect is after all not a bad thing. Otherwise the temperatures will be very, very less in the night time and temperatures will be very, very high in the daytime. Water vapor, carbon dioxide and methane are examples of greenhouse gases. In tropics what happens? You have more radiation, you have more evaporation, then you have more water vapor in the sky, right. So percentage of water vapor is very large. So water vapor is the most important greenhouse gas. It levels in the Earth's atmosphere vary from time to time, location to location, but more or less remain a constant on average over a larger period of time. Okay. So the current scientific debate about the greenhouse effect centers on the rising levels of carbon dioxide. So this rising level of carbon dioxide is man-made. The rest of the things are not man-made. Water vapor content will remain a constant. I mean, there is no way that you can increase the water vapor levels by human efforts by a very large extent, so that greenhouse effect enhances. It's not possible that way. We don't do any process which will increase the water vapor in the atmosphere. We are doing processes by which carbon dioxide is increasing in the atmosphere, of course, and methane. These two levels are increasing by man-made effects. So these are anthropogenic in nature. So these are man-made effects which have in the Earth's atmosphere. So due to sources such as burning of fossil fuels and so many other things, and such as deforestation and increasing agricultural activity. So these things have contributed to increased amounts of carbon dioxide and methane. Now we have seen that once you increase CO2, more amount of radiation is to be trapped naturally, right, and that means the average temperature is raised over a long period of time. Now this is something about, so this was something about the classification of atmosphere, let us say the thermal structure of atmosphere. We have seen the thermal structure and characterization based on the electrical properties, right. We have seen the electrical properties such as ionosphere and etc. Then we have seen the most important greenhouse effect. Right. Now at this point I will make a small curiosity question for you. So please try to look upon what is the form or what was greenhouse effect on Venus. So try to look into some books where you can find something about the greenhouse effect on Venus. Okay. Now, so this was something about the classification of atmosphere based on various types of physical parameters, based on pressure, based on temperature, things like that. So, now one important thing is, so temperature varies in a non-uniform fashion, density varies exponentially, pressure also varies exponentially, temperature varies in a zigzag, right. Okay. Now, so this is some discussion about the thermal and electrical structure of the atmosphere. Okay. So, we will stop here and we will continue this discussion based on about the circulation processes in the atmosphere of the earth. Okay.